All right. Welcome to the first talk of this month's ECHT research seminar. Today we have David Chan from Michigan State, who will tell us about some computations of the algebraic K-theory of green functors.
Great. So thanks so much for having me. Thanks for the invite. So this is about computing algebraic K-theory for green functors. So I want to start by saying a little bit about algebraic K-theory, say a little bit about green functors, and then I'll get to the computing part. This is all joint work with Noah Wisdom. Okay. So algebraic K-theory, right? You have this sort of little cartoon that I like to write down in talks, which sort of tells you what I'm trying to do. So I start over on the left with a ring, R. And I take my ring and I want to study the properties of this ring. And how do I do that? Well, I can study, maybe the category of modules over my ring or some nice category of modules like projective modules over my ring. So I go from rings to categories, and then there's, this collection of constructions which go from nice categories over to spectra. And then I produce invariants of spectra just by taking homotopy groups. I don't want to be super specific about what I mean by nice. There should be some notion of short exact sequence that is going to be sort of enough for this talk. I'm really just using the Q construction everywhere in this talk, if you know what that is. So I'm really just using exact categories basically everywhere. So for instance, right here, I start with a ring R. I produce the category of finitely generated projective modules. I apply this functor K. I get some spectrum, which I call K of R. And then I end up with these abelian groups called Kn of R, which are the K groups of my ring. There's another thing I can do also when R is Noetherian. I can start with my ring and I can consider the category of finitely generated modules, all finitely generated modules. Of course, you don't need the ring to be Noetherian to do finitely generated modules, but when you do have the ring Noetherian, this is an abelian category. And when you take K-theory, you get something which I'm going to denote by G of R, or the G theory of the ring R. And the homotopy groups, I'll write Gn of R for this. So you'll notice I'm writing my G with a boldface. This is a talk about equivariant something or other, so there's going to be a lot of G's floating around. Every time there's a boldface G, this is G theory in the sense of taking K theory of some category of finitely generated modules. Okay, so let's do a little bit here, example-wise. So what is K0? K0 always has this presentation. It's the free abelian group on isomorphism classes of objects in finitely generated projective modules, modulo this relation where if I have two finitely generated projective modules and I take their direct sum, this turns into addition. And so this is always a presentation for K0 of R. But we can get a little bit more concrete, right? If you have a field, then the finitely generated projective modules, they're determined by rank, right? This is just the dimension of the vector space, and this gives you the integers. Some higher K groups, right? K1 of a field is always the group of units. And this, you can see it's getting a little bit more complicated. You can at least start to tell different fields apart from this. And then you can K2, there's a presentation for K2 due to Matsumoto, or you can say that it's the second homology of the special linear group for your field as long as n is sufficiently large. Right? So you can see that the higher K groups, they're getting more complicated. They're also starting to see more information about your ring, right? You can start to distinguish them at K1, but also you can do things like, see that, if n is bigger than 5, these groups have to be the same thing, right? So this is really some sort of homological stability result that says that this is actually well defined. So computing K groups is hard, right? I mean, you can see, the first one I know how to do. The second one, for most fields, sure, you just subtract out, 0. But for the second one, it gets a lot more complicated, and the difficulty is getting a lot harder, a lot faster. So Quillen computed the K groups of the finite fields. So here FQ is the field with Q elements. So Q is some prime power. And Quillen computed all of these. So, you can do some computations, but of course, sort of famously, we don't know how to compute the K theory of the integers fully, right? We particularly don't know how to compute the K theory of or the nth K group of Z where n is divisible by 4, right? So K4n of Z is still sort of open and is equivalent to the Kummer-Van Diver conjecture in number theory, right? So if you could resolve these are conjecturally all 0, but it's not known. So there's still sort of a lot of complicated things that we're not entirely sure how to compute in this area. Just to say a little bit about G theory, right? So G theory, G0 admits a very similar presentation, except instead of finitely generated projective modules, we just use finitely generated modules. And instead of this definition where M is, isomorphic to Q plus K, you actually just do it whenever there's a short exact sequence, right? So you split all the short exact sequences. Secretly, this is the same relation as the projective module case. It's just that the short exact sequences for projective modules sort of already split. So for instance, if you have M and it has some sort of filtration like this, then you can show that M is this sum here of these terms. Right. So one way to sort of think about this is that you're sort of breaking off the composition series of M. In particular, if your ring is sufficiently nice, then the simple modules are going to generate, right? If the category of finitely generated modules has like Jordan decompositions, then you can see that things are generated by simple modules. Okay. So why are we doing K and G, right? So a lot of the time people like to talk about K theory because it has, tons of connections to different fields in math, right? It has connections to number theory. I sort of mentioned the Kummer-Van Diver conjecture already. There's connections to geometric topology via like Wall's finiteness obstruction or the Escobar-Bordism theorem. And there's also tons of applications. The homotopy theory, I mean, the definition involves spectra, but also considering the K theory of ring spectra, right? So there's tons of reasons to care and want to compute things about algebraic K theory. But sometimes G theory is actually easier to compute in certain cases. And maybe one reason to think that G theory is easier to compute is because the thing that you're feeding into it is actually an abelian category. So here and sort of throughout, I'm going to assume all my rings are Noetherian. And because this is an abelian category, you can run certain theorems which make certain computations easier, and this is going to be something which sort of comes back later in the talk. Um, okay, so even then, right, I have the inclusion of projective modules into all modules, and this induces a map from K theory to G theory. And I can ask myself how close is this map to being an equivalence, right? Or if I know something about G theory, what does this map tell me about K theory? And for instance, if your ring has finite global dimension, by which I mean that the X groups vanish above a certain level, certain finite level, sort of uniformly, then this map is an equivalence, right? So in nice cases for nice examples of rings, the K theory of R is actually equivalent to the G theory of R. And so if you can compute the G theory, then you can compute the K theory, essentially. Okay. So to say a little bit more about this and where this talk is going, I have this little schematic, right? If I have spectra, then I can take their homotopy groups and produce abelian groups. And if I have ring spectra, then when I take at least their pi zero, I get a ring. If you take all the homotopy groups, you get a graded ring. And if I want to understand the K theory of ring spectra, I can study the K theory of rings, and then I can ask myself how close is this map to being a comparison, or at least I have a map, and maybe knowing something about the K theory of the ring is going to tell me something about the K theory of the ring spectrum. Or for instance, if your ring is an Eilenberg-MacLane spectrum, then it's the same thing. And what I want to do is I want to apply the same idea to G spectra. So here, G is a finite group, and I'd like to sort of take this schematic that I have here and apply it to the theory of spectra with G action, effectively. Now, it's not literally spectra with G action, it's genuine G spectra, but there's sort of not time to get into all of that. Right, so as a first approximation, you can think that these are spectra with an action by some finite group G, but it's not entirely true. Okay, so what am I saying here, right? I want to replace in this diagram above, I want to replace spectra with G spectra, G ring spectra, or sorry, ring spectra with G ring spectra. But then over on the right side, I have to be a little bit more careful, right? Before I had abelian groups and rings, and now I have what I'm writing Mac G and green G, which is the categories of Mackey functors for the finite group G and the category of green functors for the finite group G. And what I have to do is I have to tell you what those are. And then I want to tell you about the K theory of green functors, and it's supposed to tell me something about the K theory of the sort of associated G ring spectra. Okay. So let's talk about the category of Mackey functors and the category of green functors and sort of try to keep this picture in mind where like this is why we're doing this, is because this is where the homotopy groups of G spectra and G ring spectra are sort of landing. So what's a Mackey functor? I'm going to fix G to be a finite abelian group. You don't need it to be abelian. You can totally do this without the abelian part. It's just easier to write the definition without the abelian or with the abelian assumption. So that's what I'm going to do. So what is a G-Mackie functor? So I'm always going to underline these things, right? So if I write M underline, that means it's a Mackie functor. If you see something which isn't underlined, it's probably a group or a ring. So a G-Mackie functor consists of, so for every subgroup H inside of G, I have some ZGH module, so some abelian group with an action by G mod H. When the group's not abelian, you need to replace G mod H with something which is actually a group, and you use the Weil groups for that. So, it's not just some collection of groups. I need to connect these groups in some way, right? If I just had a collection of ZGH modules, this wouldn't, really be that interesting of a structure. So if I have a subgroup L inside of H, I'm going to get some group homomorphisms connecting these things. So the one on top, right, if L is an H, goes from M of L to M of H, and this is called the transfer map, denoted by TR. And then you also have a map which goes the other way, right? So the restriction map, which goes from M of H to M of L, goes down. Okay, so I have a collection of ZGH modules. I have a bunch of group homomorphisms between them, and I got a bunch of relations. And I'll say a bit about where the relations are coming from in a little bit, but I'm not going to write them all down. But let's do some examples first, right? So we can sort of get our hands on these things. So I'm always going to draw these in the following way. So here the group is CP, so the cyclic group with P elements. So there's only two subgroups, so I only have two groups. I have M of 1 and M of CP. There should be an action of the group CP on M of 1 and no action on the top level on M of CP. I have the restriction map and the transfer map. And the first example I want to write down is this Z underline example, where I just take a Z at every level. And the restriction map is the identity, so multiplication by 1. And the transfer map is multiplication by P, where that's the same P as in the group CP. Right? Here, the action of CP is trivial on the integers. The action will be trivial in all the examples that I write here. Next example is obtained from constant Z. So Z underline is constant Z because it's Z everywhere. The next one is constant FP, where I take constant Z and I mod out by P, right? So I get FP on top, FP on bottom, still the identity map on the restriction, but now the zero map on the transfer. And then I have this thing called A, which is also called the Burnside. So just to show you, they're not all constant, they're not all stupid. So on top you have Z adjoint X mod X squared minus PX, this sort of relation. The restriction map evaluates X to P. It's a ring map, so that tells you where everything else goes. And then the transfer map is just multiplication by X. And this thing looks weird. It looks kind of unnatural. It's, if you've never seen this before, it's kind of a weird example to pull out. But it's interesting to us because this is pi zero of the equivariant sphere spectrum. And in general, for any group G, any finite group G, there is something called the Burnside, which comes from Burnside rings of finite groups. And it's always pi zero of the sphere spectrum. So this is sort of always a canonically interesting thing, at least to me. Okay. So I'm going to try to keep these examples running throughout. So these are good examples to have in mind, but the pictures will come back if you forget what they look like. The next example I want to pull up is the representation ring. So let F be a field, let H be a subgroup of G. The representation ring of F at the group H, what do? I take the free abelian group on H representations over the field F, so finite dimensional vector spaces over F with an action by the group H, and I mod out by the direct sum relation again. Okay. And so this gives me the groups, and I have to tell you what the transfer and restriction are. So if I have an H representation, so L is inside of H here. If I have an H representation, this gives you an L representation by just forgetting some of the action. And for transfer, I'm going to use the induced representation, right? So if I have an L representation N, I can take the induced representation, which, if you've taken a class in representation theory, almost certainly came up. But if not, you can just think about it as extension of scalars. If L is inside of H, you have an inclusion from FL into FH, and this thing is just extension of scalars along this map. Okay. And just to sort of keep the analogy running with spectra, the functor that you get when F is the field, the complex numbers, this is pi zero of KUG, right? So equivariant topological K theory, the pi zero of this ring spectrum is this representation ring here, okay? And the representation ring, I think, is sort of a good way to think about green functors. So let's just to sort of remind ourselves, right? Mackey functors were what you got when you took pi zero of any spectrum or any G spectrum. And a green functor is what you get when you take the pi zero of an equivariant ring spectrum. And the sort of extra structure that you get on a green functor is exactly what you're going to sort of see inside of rep H, or sorry, rep F. So the representation ring, first of all, is always a ring, right? If I hand you two representations, oh, I forgot to write this, I'm sorry. So if I hand you two representations, I can tensor them together, right? If I have V and W, and then I tensor them over F, this is a new representation of my group H, and this gives me a ring structure on the representation ring. Forgot to write that. I guess I erased it from an earlier version. You also get this relation called Frobenius reciprocity, right? So it's not just true that these are rings, but the ring structure is going to interact with the transfers in some very particular way. If I have an induced representation and then I multiply by m, this is always an induced representation, right? So for instance, this implies that the collection of induced representations forms an ideal in your ring, right? So this is a some interesting interaction between the transfer structure on the Mackey functor and the ring structure at every level. So the definition of a green functor is just, well, this should work, right? So you should take a Mackey functor, which is a ring at every level, and Frobenius reciprocity holds. This is not everything. You also need to require the restriction as a ring map. The transfer is additive still, but that's essentially it, right? So if you ask yourself, what is a green functor supposed to be? There's two things you should think. The first is that it's basically like a ring structure on a Mackey functor. And the second is that you have a ring at every level and you have this Frobenius reciprocity relation, which tells you how the transfers interact with these multiplication structures. I guess I should say the group actions are also through ring automorphisms now. Okay. And every example I've given you so far is in fact a green functor. So you can check this. And you can check Frobenius reciprocity if you know, find yourself wanting to. Okay. So what's where am I going with this, right? I'm thinking about the category of green functors as sort of a version of rings for my you know, these like equivariant homotopy groups. And so, I want to study these things with K-theory. I want to prod them with K-theory. And so what I'm going to do is I'm going to instead I need to think about the category of modules so that I can cook up things like the category of projective modules and the category of finitely generated modules to feed into K-theory, produce, K-theory and G-theory of green functors. So just a little bit of category theory here. The category of G-Mackey functors has a monoidal product called the box product. The green functors are exactly the monoids. The unit is the Burnside A. And an R module is just some Mackey functor M that has some sort of associative unital map from R box M to M, right? So just the definition of a module over a ring, except sort of pulled back into Mackey functor land using the box product in place of the tensor product. And the example, right, of course, because A is the unit, the category of Mackey functors is just the category of A modules. And so, sometimes if I write something like the K-theory of Mac G, it's really computed as the K-theory of A or something like that. Okay. So to reiterate, right, if you want to work with G spectra, you have to do sort of commutative and homological algebra over these green functors, right? If you want to do something like the universal coefficient spectral sequence, then you're going to take Tor over some maybe graded green functor, right? So these things, you have to sort of study these things honestly as green functors and modules over them. As another example, right, if you take the category of, so here HR is an Eilenberg-MacLane green functor, or sorry, an Eilenberg-MacLane G ring spectrum for the green functor R. If you take the category of modules over this should be equivalent to the derived category of R. So the category of modules is an abelian category, and you can take its derived category. And we want to understand these categories of R modules to sort of study G ring spectra, and we want to study the associated spectra. So just to give a definition, right? So when I write the G theory of R, I mean the K theory of finitely generated modules over R as an abelian category. And when I take the K theory of R, I take the K theory of finitely generated projectives. So I guess I should say the category of modules is abelian and has enough projectives. Finitely generated modules will be abelian when R is some kind of Noetherian. Okay. So let me sort of outline where the rest of the talk is going, I want to give some computations of K and of R for certain green functors. I want to talk about how you actually could try to compute some of these things. A little bit about what's known. So John Greenlees computed G0 and K0 of A, or the category of CP Mackey functors. He did a few more computations for different green functors that I haven't introduced yet. But I think most of them have to do with inverting the order of the group G, or in this case, inverting P, and I don't want to do that. And Thevenes and Webb also computed K0 of Z underline for some G. They sort of reduced this question to the question in representation theory of sort of things which are summons of permutation modules, I think. They sort of analyzed this question. But as far as higher K groups, I don't think there's really anything else in the literature that sort of tries to compute any of these things. But someone correct me if I'm wrong. So my plan is to sort of study this problem in the following way. I'm going to take some green functor R. I'm going to compute its G theory and compare to K theory. So I still have this map from K theory of R to the G theory of R, and I want to sort of use this map to give input to the computations. And to compute G theory, I'm going to use sort of a filtration on the category of all Mackey functors, which produces a spectral sequence, and then I'm going to analyze the spectral sequence and pull out some answers about G theory. Okay. So before I move on, are there any questions? I know that was sort of a lot of background very quickly. All right. If not, I'll get to it. So I say I'm going to use this natural filtration, so let me introduce what the filtration is. So I'm going to specialize to where the group is CPN, so a cyclic P group, mostly because the pictures look nicer and it's sort of easier to see what's going on. And this is where the computations can sort of be made most concrete. So what does a Mackey functor look like here? So you have, right, the subgroup lattice of CPN is really simple. You just have CP to the K, where K is less than N. And so I just have this sort of string of abelian groups, right? M of 1, M of CP, M of CP to the N. And I have transfers which move from left to right and restrictions which go back down the ladder. Okay. And I guess really at every level, so at the far left, there should be an action by the group CPN. In the second slot, M of CP, there should be an action by CPN mod CP, which is CPN minus 1. And so these actions also continue to sort of move to the right. All the way at the right, it's just an abelian group. Okay. And I'm going to define a filtration on the category of things which look like this. And the filtration is just FT is things which vanish to the left of T, right? So for instance, if I take T to be N, this would be the collection of Mackey functors which are 0 everywhere. So this is the 0 category. But if you took, say, F, or you take T to be 1, I guess T to be 0. When T is 0, this is just the things which vanish all the way at the left, but could be anything sort of everywhere else. Right? So this sort of gives you a natural filtration on this category. And I'm going to call this the isotropy filtration. So just to be concrete, Fn is 0, F negative 1 is everything, because this is things which vanish, which are required to vanish nowhere. And so this gives you a sort of a great linear filtration on the category of Mackey functors. And I'm going to use this to build my spectral sequence, basically. So a couple facts. You can do this for any G. Basically, it's sort of easiest to see for CPN, but you can cook up something very similar for any finite group G. So the existence of this filtration is not sort of limited by the existence of sort of a linear poset of subgroups. You can also replace the category of Mackey functors with a category of finitely generated modules over R by just intersecting the category of finitely generated modules with the filtration above, right? So you just ask yourself, does the underlying Mackey functor of one of my modules vanish below a certain level? Okay. And finally, and sort of most critically, it's important here that FM is an abelian category, and the inclusion is the inclusion of a Serre subcategory. This is sort of the observation that makes G theory important here. Because these things are abelian categories, you can really sort of start to get at these computations using G theory, and things like Quillen's localization sequence is really how you're going to produce this spectral sequence, right? So if you have some filtration of some category and you hit everything in it with K theory, As long as these are, filtrations by abelian categories, then you're going to get the spectral sequence you want. It's basically what's going on. So to be concrete, here's the spectral sequence. So as long as R is Noetherian, you need this condition for these things to be abelian when you take finitely generated modules. Then you get a strongly convergent spectral sequence whose E1 page looks like this. So remember over on the right here, this is the K-theory of finitely generated modules over my green functor. Um, and the E1 page, well, it's just take the K-theory of the sort of filtration quotients, right? Which I mean, you can take Serre quotients because everything is abelian and Serre subcategories. But of course, this is like super unhelpful right now, right? This is a spectral sequence, but if I don't tell you what the E1 page looks like in some sort of tractable way, then I can't do anything with this. Um, so of course, the next result is that I can tell you what the E1 page looks like. So, all right. So what's the E1 page look like? So remember, R here is my green functor. So I have this collection of rings. I have the transfers which go up and the restrictions which go down. And I'm going to define phi t of R to be take my green functor, evaluate it at CPT, and then kill the image of the transfer map. So first of all, what is this? This is just a ring, right? I have R of CPT as a ring, and the image of transfer is an ideal because of Frobenius reciprocity, right? This is the point of Frobenius reciprocity, is that this thing is still a ring when you mod out by the image of the transfer maps. And this thing is very close to the answer. So this allows you to compute the filtration quotients. So the category the category ft mod ft plus 1 is equivalent to the category of modules over this twisted group ring. So what do I do here? I take ft of r. This is, first of all, as we said before, it's a ring. It's a quotient it's a quotient of the green functor at level CPT. At level CPT, my green functor had an action by CP to the n minus t. So CPN mod CPT, CPN minus t. And this descends to the quotient, right? So the ring phi t of R has an action by the group CPN minus t. And you can form a group ring which may or may not take into account, which does take into account the way that this action happens on R, which is why it's called a twisted group ring. In all the examples that we've seen, actually the action is trivial, and so this is just the ordinary group ring. So, this theta that I wrote here is sort of denoting that this is a twisted group ring, but, in all the examples, you could ignore the theta and just treat this as a regular group ring. So what this is saying is that because there are equivalences like this, when I take the K-theory of this, this is just the G-theory of this ring, right? The input to my spectral sequence can be written as the G-theory of some concrete ring that you can write down in examples. And now let's give some examples because I think this phi t construction, sort of the first time you see it, is a little bit confusing to get your head around, but once you sort of write out the examples, it's actually not so bad.
Can I ask a quick question about the twisted group ring?
Yep.
So presumably when the twisting is, complicated and difficult to deal with, you take like another spectral sequence, right, from the untwisted group ring that converges to the invariant of the twisted group ring or something like that.
That's a good question. I don't know.
Okay. Me
Yeah.
neither. I just, when I see twisted, I kind of somehow
Yeah.
always ask
I think in some cases, right? So if you have like a finite Galois extension, like K is inside of L and the Galois group is G, so G is acting on L and you take the twisted group ring by this, I think it turns out that this is Morita equivalent to K, like the fixed field. And so in particular, in that case, you can actually just throw this out because K theory is Morita invariant. So sometimes you can reduce it that way, but other than that, I don't know any sort of general ways to approach that. Are there any other questions?
I also have a question.
Yeah.
So for this theorem that you just stated,
Mhm.
do you have an analog for other finite groups?
No. That's a good question. Yeah, this recognition is specific to CPN, although admittedly we didn't try that hard for other groups. So it's not that it's impossible, it's just that we didn't necessarily look at it.
I see. Thanks.
Mhm. All right. So let's write down some examples of phi t of r and get a sense of what this looks like. Just really quickly, when t is zero, there's nothing interesting going on because so when t is zero, you're looking at the r of one level, and there's no transfers which come in, so you're just evaluating at r of one and then taking the twisted group ring. So you sort of already know what's going on there. So let's look at r as one, or t is one. So g is CP. So let's look at the Burnside ring. So here's the picture of the Burnside ring, and I'm saying I'm going to take this and I'm going to kill the image of the transfer map. The image of the transfer map is just the ideal generated by x. So I'm just setting x equal to 0, and I'm taking the quotient map from this polynomial ring mod this relation to just the integers. When you take constant z, what are you doing? You're saying take z, kill the image of the transfer map. Transfer map is p, so you get fp. Right? You just get the field with p elements. And when you take constant fp, you just get the identity map because the transfer map is 0. So of course, when you kill it, you're not really doing anything. There's one more thing I want to say about these maps, right? So it's worth sort of noting here that the first map and the last map here, they both split as ring maps. Of course, the bottom one splits for very dumb reasons because it's the identity. The top one splits basically because the integers are the initial ring. And of course, the middle one does not split because you can't map FP into the integers. Okay. So why am I talking about the splitting? It turns out that the splitting is really, really helpful for analyzing the spectral sequence. In particular, if this ring map splits, then the spectral sequence collapses at the E1 page. So in particular, you know how to compute the entire spectral sequence if you can analyze this ring map. You reduce this entire question to just pretty straightforward question in commutative algebra. And something similar does work here for G is Cp to the n. For G is Cp to the n, this splitting, you have to be a little bit more careful. But I can talk more about that later if people want to hear about it. Okay. So what's the corollary? The corollary is that for A, where this thing split, and for constant Fp, where this thing split, we can compute the G theory of these things in terms of the G theory of rings, just underlying rings. So the G theory of A, which is the same as the G theory of CPN Mackey functors, splits as the G theory of group rings, right? Just this sort of ascending collection of group rings on CPT. And similarly for constant Fp, you get, in fact, the same splitting. So you get this wedge over the G theory of FP CPT. But there's another theorem which tells you that because these rings, so these group rings on FP, they are Artinian local rings. So the G theory of these is just the K theory of FP. And in particular, Quillen tells us what that is, right? So Quillen tells us what the K theory of FP is. So you can actually just write down the groups for the G theory of constant FP. Right? We sort of know what all these groups are.
Can I ask a question, David?
Yeah.
So you're getting these corollaries by the collapse of the spectral sequence at the E1 page, right?
Mm-hmm. Yeah.
So this looks like an additive like decomposition to me. Are there any like hidden extensions that show up?
Yeah. So what's going on is that the filtration is split on the level of spectra. And so in fact, it's split on the level of abelian categories when you have these maps. And so you can just, there are no extension problems because of this split.
Yeah. I see. Thank you.
Yep. Mm-hmm. Okay. So let's turn to, sort of finish up by talking about some very specific examples. So here I want to talk about the green functor constant F2 for G is C2, which is basically as small as you can get for a green functor. But this one is still pretty interesting. People sort of have spent a lot of time thinking about this guy. One way to think about it is that this is sort of talking about mod 2 cohomology for spaces with involution, right? So this is sort of a very interesting example, even if it is very, very small. So there's this theorem. I think this is due to Duggar, Hazel, and May, but if this is not, certainly they prove it. But if it's been proven earlier, I'm unaware. But they prove that this ring has finite global dimension, or this green functor has finite global dimension. By which I mean, right, that the X groups vanish above a certain level. And remember, by Quillen's theorem, and you can apply this in the exact same way to green functors as you do to rings, this implies that the K theory of constant F2 is equal to the G theory of constant F2, which we just computed above, right? So you can compute the K theory of constant F2 is the wedge of the K theory of the ring F2 with itself, right? So this K theory is now completely known because you can just compare to G theory where you can compute it using the spectral sequence. As sort of a general remark on this, back in the last slide, we showed that the G theory of constant F2 is the G theory of F2 wedged with the G theory of F2 adjoined C2. And sort of generally, right, a lot of these examples, sort of also looking at like the computations that Greenlee's did, they sort of tend to look like you're going to take a big wedge over like K theory or G theory of sort of the ground field and then a bunch of group rings. And we sort of expected that this would work for the K theory of constant F2, except that it totally doesn't. Because if you look at the corollary and you look at the sort of thing we expected to be true, they're just not the same, right? I mean, you can compute it at pi1 that these two things are different. And so this is not true, even though we sort of expected that you might get something like this. But in general, there's no way it's true because in particular, it's not true here. Okay. The other special case I want to talk about is the ring constant Z, and here the group is going to be Cp to the n. So again, here, constant Z is going to have finite global dimension. This is a theorem of Arnold, but it was sort of, he didn't state it quite this way, so it was sort of restated in this way by Buch, Stanku, and Webb. And so as a corollary again, right, because this thing has finite global dimension, the K theory of this thing is also equal to its G theory. So maybe as sort of as a moral here, right, if you sort of go into these things knowing that there are interesting examples that have finite global dimension, then you know that G theory is a good way to sort of approach these things. And so you can do G theory instead of K theory and then pull the results back to K theory. Okay. So if you look at the spectral sequence and you look at the actual groups which are sort of involved here, you can use this to come up with a computation of the K theory of Z, at least after P completion. And so the tau greater than 2 means take a second connective cover. Right, there's just a map. This is the last map in the filtration, in fact, and this map is an equivalence after P completion. The reason that this is true is because everything else in the spectral sequence is the K theory of finite fields. And the K theory of finite fields, in fact, the finite field FP, and the K theory of that is just, vanishes after P completion, basically, except at degree 0. And the reason that it doesn't, or the fact that it doesn't vanish at degree 0 is the reason that you need to take this connective cover here. In particular, you can compute the ranks of these things. So when n is bigger than 1, you can compute that the rank of Kn of constant Z is the rank of Kn of Z, the integers, which is known by work of Borel. And the rank of this other ring, the integers adjoin P inverse and a Pth root of unity. My understanding is that this is known and that this is in, like you can look this up inside of like Weibel's survey of K groups of rings of integers. I think this is known. So in particular, you can, if you had some particular one that you cared about, you could go through and you could look these up. This last computation, yeah, I think that's right. Okay. Yeah, okay. So I want to end on a couple final thoughts. So, why are we going through all this work to look at G theory, right? We have this filtration on the category of modules. Why not just like look at K theory directly by taking this filtration and looking at projective modules and using this to study K theory? I think this is a totally reasonable idea, and this is what we wanted to do. But it doesn't work because projective modules just don't vanish anywhere, right? The way that projective modules look, or the way that they work inside of green functors, they just never vanish anywhere. And so while you get a filtration by sort of intersecting projective modules with the isotropy filtration, the filtration is really dumb because they're all in one spot. And so there's just sort of nothing helpful to be said there. The other thing I want to say is that we know the K theory of uh, compact G spectra splits as sort of this big product over the conjugacy classes of subgroups, so the K theory of these spectral group rings. This is a result of Rognus, I think. It's so the sort of natural question to ask is the K theory of the category of Mackey functors, does this also split? Right. And as the product over conjugacy classes of subgroups of the K theory of these integral group rings. Um, I I really believe this should be true, but I don't know how to show it's true. So I just wanted to sort of throw that out there. And if anyone knows how to do it, feel free to let me know. Okay, I think that's all I've got. So thank you for listening.